So we want to make a commit. Sorry, hold on, Kaushik. my earbud popped out. Okay.
No problem. The joys of recording.
Oh yeah.
From the Spec Network, this is Fragmented, developer podcast where we talk about building good software and becoming better developers. I'm Don Felker.
And I'm Kaushik Gopal.
Welcome to the show.
This episode of Fragmented is brought to you by educative.io. Now, there are a lot of websites out there that help you teach programming courses, but one thing most of them tend to do is focus on video, so they're all video-based. Educative.io takes a very different approach. To them, they go the text-based route. That means you don't necessarily have to scrub back and forth to follow along. Say, you're going through a video and someone just blows past a certain section, and then you're going back, wait, what did they say exactly? And you rewind, then open up a notepad to take notes. You don't have to do any of that with educative.io because it's text-based. Think of it as almost reading a book. If you're reading a book, it's pretty easy to skim back or double back and just easily skim through. In addition to a whole bunch of amazing courses out there, here's the kicker. If you're an Android developer, they just launched a killer Android course called Modern Android App Development. It's perfect. Just go back, refresh your memory, and go through the educative course. It has a fully functional live Android emulator, so you can actually create and deploy your app right from within the course. You'll get a live link to the app that you can share with friends or even, put up on your portfolio if you start looking for jobs. Check it out now and get an additional 10% off your purchase if you go through this special link, educative.io/fragmented. Once again, that's educative.io, educative, in case you didn't catch the spelling, educative.io/fragmented. Thanks again for sponsoring this show, Educative. All right, folks. So sadly, Don couldn't join me today for this show, but I do have someone else who's joining me, and I'm super excited about this guest. He was my boss at a previous job. He remains a mentor to me today, and I always go to him when I need, in general, software engineering advice or heck, even life advice sometimes. So I'm really excited to have him on the show and have you folks talk to him. He's easily one of the best engineers I've ever worked with. So without further ado, I'd like to introduce you to Gordon. Welcome to the show, G. How's it going?
Hey, Kaushik. Oh, it's very exciting to be here. Thanks for having me.
The funny thing is, folks don't know, but we even talked about starting the podcast at at an early stage when, back when we were at Wedding Party, we talked about the podcast. So you've actually seen the podcast from the day it was created to around 197 in. How crazy is that, huh?
That's right. Yeah. We talked about, there was iOS podcasts and Rails podcasts. Oh, but there's not an Android podcast, and there needs to be one. People need to learn how to do this stuff.
Yeah, Android developers also have commutes, and we needed something to listen to.
Yeah, yeah, exactly.
For folks who don't know you as well as me, could you just let us know what you do, where you work? Just give us a brief background before we jump into the meat of today's show, which I'm super excited to get to.
Sure. So I currently work at the same company that you do, Instacart. And the reason is that both of us joined there from Wedding Party, which is our previous company. And that was a venture-backed startup in the mobile space that I co-founded with some friends. And we managed to convince Kaushik to join us, which was an excellent thing. And prior to that, I was at Carnegie Mellon in the Silicon Valley here, doing grad school. And before that, I'd been doing some software engineering for some professors. So I've been doing software engineering for a while, and I've been working with Kaushik for a while.
For better or for worse?
Not for better, for better. Yeah.
So I don't know if you remember this, G, but back at Wedding Party, when one of our new colleagues joined us, whose also like you, who's a very good friend of ours now, when you were doing her orientation, I remember she was pretty early on in her career. So you were basically doing like a walkthrough of Git, because we used obviously Git for our version control. But I remember like the orientation session you were doing for her, because I mean, we were like huddled in like a relatively small space, right? So like I overheard how you were doing like some of the Git introductions to her. And I thought it was fantastic, because what you did was typically the way people learn how to use Git is, they just Google like a cheat sheet of sorts or something along those lines, right? So they find a cheat sheet, look at the commands that they've been using for some time, just like, just repeat those commands you find on a cheat sheet, and then you get 60% of the way, you start using, and then eventually you start to maybe understand. But a lot of developers go a long way without even understanding the internals. You flipped it though, like when you did this orientation, you almost made sure to explain how the internals of Git work. I thought it would be amazing if we can like almost go through like a mini orientation session where like you can talk to us about how the internals of Git works. How does that sound?
Yeah, that sounds great. Yeah, I remember when I was learning Git, I had that problem where at first I was looking at the commands and trying to figure things out. And I really just had no idea how to use it and why these things were the way that they were. And it was only, I read a couple books about it. And finally, once I understood the object model and what was going on there, then what they call the porcelain commands, right? The fancy commands that you use on top of this stuff, they finally made sense to me, right? So yeah, I'd be happy to dig in.
Yeah. So you mentioned something, and again, for folks who know Git, this would like ring a bell, but otherwise it sounds like just like, off the cuff fancy term. You said porcelain. I know Git has like this thing where there are like two kinds of commands, right? There's like porcelain commands and what's the other one? Plumbing or
plumbing. That's right. Yeah.
Okay. So what exactly is porcelain and what exactly is plumbing?
Yeah, so the porcelain commands are the commands that you typically will use in your day-to-day development. The plumbing commands are commands that are there for people who want access more to the internals. So they'll use them for like writing scripts or for sort of custom workflows that you typically wouldn't otherwise use.
Interesting. And what are some examples of like, porcelain, and like what are some examples of like plumbing commands?
Yeah, so like, git status would be, or, git commit would be porcelain. For plumbing commands, there's git cat file, which will, print out the contents of one of the blobs that's in the object directory, for example.
Oh, wow. So there's git cat file. So this isn't like the basic Unix cat. This is like, Git has a variant of cat in itself that actually like gives you like maybe more information.
Right. And the reason for that is, so if you look at Git, there's this directory in your current directory. It's a hidden directory called .git. And if you go down under there, there's a bunch of files in there. And one of the directories underneath that is called objects. And if you look in there, you'll see a bunch of, short folder names, and then under there you'll see some longer name files. Mm-hmm. Those files are objects, and they're different types of objects, and they're actually the contents of those is the file content itself, but you can't look at it because it's zipped and it has a header on it. So trying to see the content of that file, you need this thing called git cat file to actually tell you about the file. So you can send it a couple of flags to have it either show what the type of the file is, or the content of the file.
So we're going to jump into the Git directory, but like I want to actually step back even before that, right? Because Git is a little different from like most other versioning systems, right? Because I don't know if you've probably worked with some of the older ones, right? Like Subversion and Mercurial is again like slightly newer. It was like the competing thing with Git, but there was like a couple of versioning systems before that.
Right. Subversion.
Yeah, can you explain how they're like, because I remember like with Subversion, like, your versioning used to be 1, 2, it used to make a lot of sense. It's just like version 1, 2, 3, 4, 5, 6, that literally that used to be the version, which seems crazy in today's world because people are so used to Git. But what's the deal with that? Like, why did Git have to make things like that much more difficult for like us, right? Why couldn't they just like use something as simple as what Subversion did. Like, what is different about Git? Like, why was Git such a revolutionary thing? Was it just like the new cool tool to come out?
Yeah, so the thing with Subversion was that it was kind of like a centralized database, right? So there was a monotonically increasing version identifier. And as long as you were talking to that centralized database, it could easily sort of increment as there were new versions. That doesn't work so well if you have a decentralized platform like Git. So Git, you can actually, you can do Git locally on your local machine, and then everybody can, after the fact, decide to join with some centralized Git repository. And so what you need to be able to do is basically do offline work separate from the repository, and then everybody can reconcile that stuff after the fact. So there's no like centralized version number that people can use. Instead, the way that it works is that everybody agrees on the identifiers for the data that's in their system, as opposed to having a version number. So the same file will end up with the same very long SHA, and that's where the agreement comes in. Yeah.
Oh, yeah. So like part of it is like, and use some terms, you said like centralized versus decentralized or like distributed or something as well.
Right.
And that's why it works so seamlessly, where you don't need to be connected to the internet. You can just keep using Git, right? And I remember like with Subversion and stuff, you couldn't actually at that point. Yeah, you can. I mean, eventually, I think even with Git, when you push to like a remote or something, you need to connect to like a central system. So when we use GitHub, which is like different from Git, does GitHub also function as that centralized thing? Or is GitHub just like another client that like listens? If you're doing that, why isn't it the same as Subversion? Like, you know what I mean? Right.
Yeah. Well, the interesting thing about Git is that remotes are not particularly special. So in Subversion, it's your database, right? It's your centralized repository. But in Git, remote is just another repository. So what these things are called remotes. Origin is just sort of a standard name for one of the remotes. But you can have many remotes. Like I remember when I was first deploying to a thing called Heroku. Heroku also took a Git repository, and so you would set it up as another remote. And I think most people just called it Heroku.
Oh, that's right.
So you would say like Git push to GitHub, but then you could also say Git push to Heroku because it was just another remote.
Typically, Git push origin is what most people are used to when they want to get their work up to like a common report, right? And that repo, and that typically tends to be GitHub. Yeah, but that makes so much sense when you put it like that. So with Heroku, you have like an equivalent repository, just like how GitHub probably has. They have a repository, and you're pushing to that remote. So it's like just another place.
Right. And there's some smarts around it because it uses the Git protocol, and so there's some work that's being done on the server side as well as on the client side when you're doing these. But without that protocol, you could rsync files if you needed it. It actually, no, it wouldn't work very well. You really want to use the Git protocol. Yeah.
Okay, that's awesome. So yeah, and I pulled this out of this, but I want to jump right back in. You said there's a .git directory, right? And like this is the funny thing, because when people usually type, when they git init or like they create a new repository, like everything looks normal. Nothing looks like it's crazy. If you have a fancy shell, it just shows like master suddenly. But the smarts and like all of it is in that .git directory, right?
Right.
But what exactly is stored in that .git directory, right? Like, is everything stored there? So like if I accidentally just delete that directory, am I just like nuking my whole Git repo? Like
that's right. That's the one thing you want to avoid doing again. So yeah, you'll nuke all of your history. That's right. So that's one reason for wanting to have stuff up on GitHub for sure.
Oh yeah, that's true. Yeah, because at least then you have somebody else who's. I wonder, is this how like torrenting works? Is there like a similar theme about how torrenting works? Because like there's no it's like decentralized, right? Oh, I guess it's probably just decentralized, but it isn't.
It's actually pretty centralized. It's decentralized in the fact that you have a full copy of the repository, and also GitHub has a full copy of the repository. but it's not quite the same as torrenting, where the data would come from many different computers.
Oh, that makes sense. Oh, that's right. Yeah. So no single person. Torrenting is a little more like, it's interesting for different reasons, because like I think it's like, oh, I have these parts, you have these parts. Like let's exchange
Right.
and then build our copy so that we can eventually reach to a point. But the summation of everyone like who's connected should at least have some piece, right? That's how like we know.
Right.
Got it. Oh, okay. That makes a lot more sense. Cool. So well, what exactly is the structure of a .git directory? Like, what would I if I opened up my Git repo, like .git? I just open it up for like a newer repository. I see objects, I see refs, I see like a whole bunch of things like hooks. Can you like walk us through what exactly is stored in each of these things?
Right. So initially, it starts off relatively bare bones. So it'll have a hooks folder, which has a bunch of examples in it. And these hooks are basically things that can fire off when you do a commit. For example, it can, you can put some checks in there that ensure that it abides by some strictures that you have. And if it doesn't, then it says, hey, I'm not going to commit. There's the objects file folder, which we can talk about sort of in greater depth. There's a thing called refs. And actually, there's sort of a minimal amount of stuff in there when you first start. Things start to get interesting once you add more into there. So we can talk about what happens when you actually make your first commit. And the stuff that goes in there. Yeah. So the first thing you do when you are working with Git is you'll have some files. Let's say you got one file and you decide to stage that file. So you stage it, that goes into the index. And when you put a file into the index, it actually also it creates files inside the objects folder. So it basically takes the contents of the file and it adds a header to it, hashes that, and creates this really long file name and sticks that into the objects folder. And then it also puts it into the index, basically a reference to that file name and data about it. Then you have that sort of sitting there, but there's no commit yet.
You said index. There's like an index, but that isn't yet committed, right? Like, so how do I, this is like when I do the git add command, there's like this temporary middle ground where it's almost like, and that's why I guess it's called like staging, because it's like, oh yeah, let's just like make sure everything is fine before we hit the button and then like, boom, get it out there.
Yeah. I mean, it's really helpful, right? Because if you have like lots of changes locally, but you really only want there's like a logical set of them that makes sense to land together. And then maybe some other stuff that you didn't want to land. It makes sense to put that stuff into the stage and then say, yes, these are the things I'm going to commit and the other things I'm not going to commit.
Oh, interesting. So say like I've worked on a feature and I have like a bajillion files, but I was like, for the sake of like maybe a cleaner history, or you don't want like, or there's another like some folks have this thing like every commit should pass the build or like have a test. Like some people have like those kind of rules, right? So if you want to stage it together so that like, okay, I want to plot these changes and then commit a different portion. So that it's helpful in those kind of scenarios, right? Like where you don't want the whole thing to just go into a single commit.
Exactly, and you can always revisit your history after the fact by sort of doing a rebase and moving things around. But it also makes sense to try and stage and commit things in reasonable steps so that you can sort of follow along, or somebody can follow that along in a PR. So that's a reason why people use the stage.
The funny thing I realized, and you can correct me if I'm wrong. In say I'm like watching my .git directory, right? And I add something to the index and then I commit it. If you look at the .git directory, you may not necessarily, I mean, there'll obviously be a difference, but there isn't like an indexing area where it's like, oh, this is temporary, right? So it's the whole temporary staging thing is like a conceptual thing. It like to Git, it's literally just another step, right? Where it does like the hashing thing. And we'll get into that in a moment, where how those objects are stored and hashed. But there isn't anything special about like adding to the index, right? It's just like, it's it's just a conceptual thing, right? Is that right or not exactly true?
Yeah, there actually is this index file that's so it's in the .git directory. It's called index. It's a binary file, and
I see that. Yeah.
yeah, and so you can also you can get access to the contents of that by using git ls files, which is another one of these plumbing commands that we talked about, and so you can see what's in there, but and it's basically just a list of file names and the SHAs that represent those file names. So it does get added to that.
Oh, so when I do a git status, it's typically like looking in the index file and a bunch of other places before it gives me like the status.
That's right. Yeah, right. It needs to look at your local working directory and to see the untracked files. It needs to look at the index to see what's indexed, and it will also look at the commit to see if your changes are in the index are different from the ones that are in the latest commit.
Interesting. Okay, so like the objects thing now, right? Like how does that work? Like, and can you like walk me through like the simplest thing? Like say I'm creating like a dummy file, right? Like a text file, like the simplest thing, like, because we're going to get into also like, because you can commit anything into Git, right? Like you can commit videos, like heck, audio files, like
any file. Yep.
I'm curious also about that. Like how does that happen? But like we'll get to that in a bit. Before that, how does this? Yeah, like if you walk me through like the simplest like text file, like say I touch, like which is a Unix command for just like creating a file, or like heck, I just in your favorite text editor, I create like a text file. Can you walk me through what happens from the point of adding and then committing? Like internally, what would the Git directory like see?
Sure. So so nothing will happen at all until you actually add it to your index. When you add it to your index by doing git add file name, what will happen is what's called a loose object will be created. A loose object will go into the objects directory. Now, this is that funny thing that where the contents of that file, along with a header, will be hashed, and it'll make this 40 character string, right? It's a hexadecimal string representing the data. And then it takes the first 2 characters of that string and determines which directory it should go into based on that. And then the remaining 38 characters become the file name underneath that directory. So that content is then added to that file, but it's zipped first. And then, so now we have there's a new file inside the objects directory that is addressable by the content. So it was the stuff inside the file that made us decide on what the name of the file should be.
Got it. And no 2 files. Well, if I had the exact same file, it would also basically hash to the same thing.
Interestingly, it's actually, if you had the exact same file content, it'll go to, so it doesn't even matter what the file name is or what the permissions are on the file. All that matters is the contents of the file, which is great because it dedupes exact same files.
Oh, this is like very interesting. If I had like a 10 MB text file and I kept making changes in, like, I was changing one line, and I have a Git log. I've changed that file like 100 times. It doesn't store 100 copies of the same binary, right? Like assuming like nothing changed about the file, right? Like I just was like changing the permissions or something. It doesn't actually, if you actually make changes in the file, I would imagine it's storing like, how does that work? Like, does it store different copies? Does it diff those copies? And also,
Right. So if you're changing the permissions or the file name, either one of those, it won't make any changes to the to the blob associated with that data at all. If you then stage and commit that file, it will make changes to what's called the tree that points to the blob, but it won't make changes to the blob. So, but let's talk about the tree a little bit later. Yeah. So it won't make changes to the blob. You're right. If you do make changes to the contents of the file, then because the contents is different, when you hash that contents, you get a completely different hash. And so it'll describe a completely different file name. And so it'll even put it into a different directory, since the directories are the first 2 characters of the hash.
Oh, interesting. And so that basically means I will have like new 10 MB files like
Exactly. Yeah, you'll have many 10 MB files, which is a kind of a crazy thing. And so that's why these are called loose objects at first. And so it'll store loose objects for a while until it decides that it needs to automatically kick in and do garbage collection, which will see all these different but very similar files, right? And then it will create a thing called a pack file, and the pack file is the optimized format that you're probably imagining this stuff should go into.
Can you spell that out? Packed file as in PACT or PAC?
Yeah, it's PACK file. So it's a very sort of tightly compact file, and there's a separate file that's the index into that file. And so a pack file works by basically it stores like the latest version of the file fully, and then the differences are from the previous version are stored after that. And so when you look at if you want to determine the contents of the file at any given time, you'll look at the index for that. But what's interesting is that doesn't happen at first. At first, you just end up with these loose object files. So you'd have many 10 MB files within your objects directory prior to that GC happening.
Oh, wow, I just had a mind-blowing moment right now. I remember when I work on very big repositories, sometimes Git just tells me to run Git like GC, like garbage collection, and I'm like, whatever, okay, just run the command.
Yeah.
I see, because I just let me commit, like, because it won't, like, sometimes Git doesn't allow you to commit because it like gives you warning saying like either you have too many loose objects, which again makes a lot of sense.
That's what those are. Yeah.
Got it. Okay, so I just had like a major aha moment right now. Okay.
Yeah.
So I noticed there's actually a directory in objects called pack, which I guess is where like all the pack files. So if I want to see those pack files, that's probably where it would be stored, right?
Right.
Okay, cool. I'm with you so far. So there's like loose objects. We're walking through this, like there's different 10 MB files. What happens next?
Okay. So what happens next is we have those files as loose objects in the object directory. And that's like the first thing that happens when we're doing the staging of this thing. The next thing that happens is we put the content into the actual index file. And what that does is basically we have the SHA of the file, and we want to say what file name it's associated with. And so that information, sort of the combination of that information, goes into the index. Let's sort of skip forward now to what a commit looks like, because a commit is sort of this is the crux of it. This is where things get really interesting. We have these sort of loose objects just sitting there with these really long names, right? And that's kind of useless to us unless you can translate a file name into that. So we want to make a commit. So we have a file that's this sort of loose object now. And in the end, we want to have this commit where it says, this is what my directory looked like at this time, and here's basically the SHAs of the files at the time that I made this commit. And so to do that, if you sort of work your way downwards, you want to have a commit object. And that commit object needs to somehow describe all the files that it had. And we know that there's these SHAs that describe the files, the content of the file, but we need to know the name of the file as well. And so what this commit does is the commit points to a root of a tree, and this tree is a new type of object. The tree object describes the top level of your directory. So in this case, it's actually pretty straightforward, because our directory, let's say our file name is example, right? The tree object just has, it'll have something describing the permissions on the file or the mode, and then it'll have the file name, and then it'll have that 40 character thing. So it's very simple for this particular example. But let's say that we had a subfolder that also had a file in it. This tree would point to another tree file. And that tree file is an object inside of the objects file as well. So it also has this 40 character name too. So the key thing here is that in the objects folder, we have commit objects, we got tree objects, we got blobs, which are the raw file storage, and we also have sort of annotated tags. But let's just ignore those guys. But yeah, we've got 3 different types of things that are in the object folder, and they all use this SHA structure.
Andrew, so that was the thing I was going to ask. If I open up my objects folder, I'm not going to see like tree objects, loose objects, blob objects. All I see is like, say I had like this 40 character sized sort of thing. I see directories with just the first 2 characters, the first 2 like characters off that long string as the name of the directory. And then the rest of the portion is hashed and then stored as files inside that, right? And like, that's the only thing I see.
So if you were to go to one of those files and unzip it, you'd see that the first line of the file describes the type of object that it is. So it would either be a blob, a tree, or a commit. That would be like right inside the first line of the file.
Got it. So the type of Git file it is or whatever. Yeah, the Git commit file.
Yeah.
Okay, got it. Yeah. All of those commits basically. And depending, I obviously can't tell from just looking at the directory listing, but obviously Git can. All of these are just like interspersed in the objects directory. So any of those things could be like a tree object. It could be an actual file object, or it could be just like the info object thing.
Yeah, it's just kind of like a key value database addressable by the content of the file.
I was going to ask that. So how does the deduping work here now? Because Git just like is able to search through all of these things and find out if that same hash exists, and just for that file content alone, and then it just points to that. Like, and that is just zipped together in like the different commit. Is that how it works? That's how it's able to do the deduping?
Yeah, the deduping works because all it cares about is the content of the file. So when you're let's say that you have like a license, for example, and you put it into like 5 directories, and it's the same license, right?
Right.
When it's deciding how to store that file, the first thing it does is it takes the content of the file and it hashes it. And that hash will be the same for all of the licenses because they're all exactly the same content. They're in different places within the repository, within the working directory, but they're the same content. And so the thing that will differ about those when you actually look at the commit, if you work your way downwards from the commit, is that they'll be in different trees, but the tree will point to the exact same hash for all those files.
Got it. So the tree is almost like the binding metadata thingy, right? Like that
exactly.
Is able to like pick the metadata and then know, okay, so this is how I should construct my directory.
That's right. Yeah.
So before we like go into like more topics, let's talk about the hashing thing. So like, what's the deal with the hashing thing? Like, so this is an SHA-1 hashing algorithm.
That's right. Yeah.
Any reason why that was chosen? Like, or is just convenience? Like Linus just felt that I have this, and I also like in the recent past have heard there is like something to it where like there was typically no collisions, but apparently I was reading like this thing where like the first collisions ever happened in the history of Git, blah, blah, blah.
Oh, interesting. Yeah.
We want to be changing this to a new algorithm, but the changing that is not that straightforward, but like it's not really that big of a problem if you have a smaller... what's the deal with this hashing algorithm?
So I'm not an expert on this, but what I think must be happening is that you want to find a hashing algorithm that has a good distribution, right? Because you want to make sure that... If you look at your objects directory, there's 256 directories underneath it once you have enough files, because the first 2 characters of hexadecimal can describe 256 directories. If you look inside those directories, they're distributed. The files within there, especially on a very large project, are distributed almost equally within those 255 directories.
Oh, and that's the virtue of the algorithm, because like this is the thing where like even if I change a single character in my text file, the hash looks like very different. It isn't like, okay, in that 40 characters, hypothetically,
Right.
say all the characters were 00000, right? Like it's going to be very rare for you to run into that, but whatever. Like even if you run into that, if I change one text character, it isn't basically going to say, oh, I'll change one of those zeros into one. The hash.
Right. Everything changes. Yeah.
And this is, I think, what you mean by distribution, right? So it like spreads it across those
Yeah.
characters. Okay.
Yes, that's right. And the other thing is that you want it to be, so you want a good distribution. You also want to be able to have it sort of uniquely identify the data within the file as well. So what I mean by that is, kind of what you were saying before, the first collision. Like you really want no two files to possibly, with different content, to possibly ever have the same SHA. So that's part of the reason why these things are so long, right? This is supposed to be like universally unique fingerprint for the content of the file. So if you have the same file and I have the same file and we put it into Git, we'll end up with the same fingerprint for it. But no file that is not that same contents will have that same fingerprint. So we can know that this is always going to be the same for absolutely everyone, and that nobody's going to disagree with us because it's so long. Now, what's interesting is that when you're working with Git on small projects, when you do like Git log or whatever, what you'll see is these sort of very short SHAs. It doesn't show you all 40 characters. It shows you like 7 characters or something.
Oh, that's right. Yeah. That's the other thing. Yeah, I'm curious about. Yeah.
Yeah. So, both of us work at a company that's like now getting pretty big and has a lot of commits, and that the number of characters that show there, it seems to be increasing over time because there's potentially more collisions within the data itself at those small numbers. Yeah.
Oh my God. Here I was thinking that was because I had like some weird setting on my computer because I keep messing up with my Git config and stuff.
Well, it might be too. They may have also changed Git, but fundamentally, there's a problem with collisions. Imagine that it only showed you 2 characters, right? that as soon as you had like 255 files, you'd accidentally be or even before then, there'd be the likelihood of some collisions. So it needs to show more than that. If it showed all 40, there'd never be any collisions, but nobody would actually want to type that.
Right. So Git is really smart to show just enough so that it's like unique for within, like no 2 sets of what Git shows in your log would be unique in your directory, in your like set of commits at least.
Right.
Damn, that's pretty smart.
Yeah. I feel like we should at some point talk about refs too, because so far all we've been talking about is these SHAs, and nobody wants to work with them, right?
Yeah, let's do it. Yeah, let's talk about refs.
Yeah, so refs are basically like these nice things that help us work with these SHAs. So there's this idea of branches in Git, and there's the master branch, and it's again like Git is kind of interesting. Master branch isn't really special, except that it's the branch that happens to be created when you do a Git init. Otherwise, there's nothing. And by convention, people say, "Oh, okay, well, master branch is like trunk for development."
Right, it's like your default, basically, right?
It's your default, yeah. But other branches are equally valid, and there's not really any difference between them from Git's perspective. So if I make another branch that's called, like a feature or something, then the two are pretty much indistinguishable from Git's perspective. And the reason I bring that up is because branches are basically they're one of the things that is a ref. So a ref is basically a pointer to a commit. So in the case of master, right? Master, when you say master, it's actually put into a folder in Git called .git refs heads master, and if you look at the contents of that file, that's a file that's actually, you can just look at the content of it. You don't have to use any kind of special tooling, and it just has a SHA in it. And that SHA points to the commit that it believes is currently master.
Oh, interesting. So it's literally just a reference. It's like straight up a key saying like, oh, if I go to this branch or like this reference, what is the commit I should point to? And then that basically just stored in that.
That's right. Yeah.
Oh, interesting. Okay, so I'm actually just looking at this, and it's you're right. It's in .git/logs/ref.
Oh, logs is a different folder. Yeah, it's in .git/refs.
Oh, that's right. There's another. Oh, you're right. There's another .git. There's a refs there as well. Damn, that is yeah. And I also see the tags, which is like again like a different thing. But okay, so ref stands for references, and there's nothing magical about this. That makes sense. So what you're saying is, as I create new branches, say I create like a feature A branch, there'd just be another file like master in my refs heads directory where it would create a new branch. It would create the new branch. It would create a new file with the name of the branch that I have, and it would literally just point to a commit.
That's right. Yeah.
I don't want to like be jumping too much, but I've run into situations where I've found that I'm on a commit, but my status doesn't say that I'm on that branch. It just points to commit. And this is because it has like that weird message where it says like, oh, it's not loose objects. I forget what like Git tells you. It's basically like, oh, I can't find the...
Yeah, it's a detached head state.
Yes, detached head state. What's the deal with that?
Yeah. Head is another file that's in the .git directory. And head is kind of interesting. It can contain two things. It can either contain and if you go and look at it right now in your .git directory, you'll probably see something that looks like, ref : and then the name of some ref.
I see it. Refs heads master. That's what refs/heads/master is what I see.
Yeah. So head basically describes the commit that you're currently looking at. And so right now in your working directory, the commit that you would be looking at is the same commit that happens to be the master commit. But you can check out a different commit that is not pointed to by any of the refs, right? So it's not pointed to by master. And if you do that, this head file will update. And instead of saying ref : something, it'll just have a SHA directly to the commit that you happen to be looking at.
Oh, interesting. So there's like different things here. I could be in different branches. So those are different references. So it could be feature A, feature B, or just master. So I could point at any point. I could be on any one of these branches. And so there's like something that points to that. And then even inside one of those branches, I could be in any one of the bajillion commits in that branch.
Yeah. But what's interesting to think about here, Kaushik, is that if you let's say you're on your feature branch, and you say git checkout head and then a caret, right, which will move you to the previous commit. Then the question is like, are you in the branch or not?
Yeah. Oh yeah.
You're on a commit.
Right.
And you're sort of still in the branch by virtue of being in the descendants of in the ancestors of the final commit of the branch, but you're also kind of not in the branch, right? You're on a commit
because there's no ceremony to like this whole branch thing. It's almost like a nice like handy like sheet for you to like quickly jump. It's like a convenience thing. The commit in the end is like the main thing, right?
Yeah.
And that's disambiguated by this head directory and the refs thing that we have there.
Yeah.
So if I'm feature A, I'm on branch feature A. Okay, so I say I'm like 10 commits before, I've checked out a 10 n-10 commits, right? Like where n is like the tip.
From the branch pointer?
Yeah, from the branch pointer. How does Git know that? Like where would it look and how would it like disambiguate that?
It doesn't know it. The only way that it would be able to know it is by going to the pointer for the branch, which is 10 commits forward, and walking its way backwards to the parent commits until it arrives at where you are on the head, and then it would say, oh, that was 10 steps.
But so here's the thing. Okay, so I'm there. Now I switch to a different branch, right? I switch to master and I switch back to that branch. It doesn't take me forward. It keeps me at that same tip. So how does that happen?
It would actually take you forward. It would take you. So if you were on feature A and you move 10 commits backwards by doing a checkout 10 commits before, and then you check out to master, and then you check out your feature again, you'll be at the reference to your feature, not at that 10 commits backwards. Yeah.
Got it. Because Git, it's almost like an alias, right? Like the
yes, branches. It's exactly like an alias. Yeah.
Interesting. So if I did check out 10 commits before and I wanted to stay there, then I would have to reposition the head of that branch to point to n-10 commit. Right.
And that's pretty straightforward. So all you need to do in that case is say git reset hard, and then the name of the branch that I'm sorry. What you would want to do instead is be at the branch pointer and say git reset hard, and then the name of the commit that you want to reset the branch pointer back to.
So what happens then, though? Because I know there's another very interesting command, but if I do that and then I go to I jump around, work on master, work on different feature, and I come back and I'm like, crap, I wanted to go back to that place that I'm in. I know Git somehow has this. How does that work, right? Have I lost that for eternity if I just reset? Because the other thing is, in my early days of Git, people used to scare me saying, do not do git reset hard origin master, right? Which is a command which is basically nuke everything and then get me to this point. But then I also realized as I learn Git, that's, if I commit something, I don't actually have to worry about anything because you can somehow always get there. How does all of that work? And actually, I think you were the one who taught me this command.
Right. So there's a thing called the ref log. And when you do git ref log, it will just show you everywhere that you moved to. So or where the references moved to. So for example, if you went to one commit and then you changed the pointer to another commit, every piece of that information will be in the ref log, and you can sort of work your way through the ref log and see which commits were being pointed to at which times. Then you can say, oh, that's the commit that I want to get back to. And so, you can then say, git reset hard, and then the name of that commit, and your branch will be back to pointing to the commit that you were on at that time. And nothing is lost in Git that's been committed up until it's garbage collected. And it's garbage collected only when nothing points to it anymore for some duration of time, or you say, please prune it.
Is there a difference between Git pruning and Git GCing? Does GC and prune basically do the same thing, or no? There's obviously some difference.
I actually don't know.
Yeah, well, that's homework for us, I guess.
Yeah, exactly. Yeah, I think prune is one of the flags for Git GC, but actually, I'm not sure. Yeah.
Honestly, half the time with prune and GC, I'm just copy pasting. I see a command, I was like, okay, Stack Overflow this. Someone says run prune or GC. I run it and it gets me through. So that's, yeah.
Right. But if we talk about this real quick, if you make a new feature branch and you make a bunch of commits on that feature branch and then you delete the feature branch, what you're deleting when you delete the feature branch is just the ref to the branch. Those commits that you made will still be there, because the commits are inside the objects folder. There's just nothing pointing to them anymore.
I see. So, and again, this is to be clear, this is only on your machine, right? So that means
only on your machine. Right. Yeah.
This isn't there's no magic synchronization happening. When you push, it looks, in the end, it does look at the branches that you have or the refs that you have, right? And
right. It will only push the information that's pointed to by refs. That's right. Yeah.
Got it. Okay. So, but you still can get to it through git ref log I see. That's what you mean. So if you haven't garbage collected that, it's on your local, because by virtue of having moved to a whole bunch of different places, it keeps track of that. But it isn't deleted until you prune. And when you prune, it says hey, nobody's pointing to that, so I can save some space, nuke that out of the local, and then it's lost.
Exactly.
Got it. So does that mean if we're working in the same repository, clearly your ref log is going to look very different from my ref log, right? Because
absolutely. Yeah, that's a local thing.
That's a purely local thing. Okay, got it. This is making a lot of sense to me. There is one question I wanted to ask. So like with respect to the deletion thing, right? What happens if I actually delete it? Like, because I'm like in my repository and I'm saying, nope, I don't need that asset anymore in my Android directory. I want to design is giving me a new asset, or like, heck, that feature didn't work out. So I'm going to delete something.
Right.
I'm actually RMing that file and committing. Does Git actually delete it? Like, what's the deal? There, what happens in that process? Because when I pull the repository again, I don't see the file, so like when I list that file, I don't see it there. So
your working directory, the file is actually removed from your working directory. However, if you think about it, like let's say you delete the file and commit, but you need to have that file if you happen to check out the commit prior to the commit you just made. You need that file to sort of reappear, and so the file needs to stick around inside the objects directory.
In our original thing, the 10 MB thing, this is again like another reason why it's stored in there, right?
Yeah. But it'll So the objects directory can grow quite a bit, and in fact, even like it won't even garbage collect that as long as let's say we were working on master when we deleted it. If you walk your way backwards on master, that file will still be needed by some of the ancestor commits, and so it can't remove it from your objects. Now, there's a command called filter branch, which is used for actually removing files from the Git commit history as well. But I'm not super familiar with what it does. What I do know is that there's no way of changing a commit in Git without also changing the SHA of the commit, which makes it a new commit.
Right. So there's only a moving forward kind of approach here, unless you have to change the history altogether, right?
Yeah. The whole history would change. So it would none like if you were to filter a branch, none of the commits after where you remove this file would have the same name that they used to have. They would all have a different SHAs.
And this is because the tree, like one of those tree objects has changed, and then that reflects all the way up as you move
exactly, because you think again, it's the contents of the file that's the name of the file, and so if you look in a commit file, the content of that file will change because the SHA of the tree is different, and that's inside the commit. Yeah, so it'll end up it has a sort of a cascading effect when. Yeah.
Damn, that's fascinating. Just to think that Linus actually thought about all of these things, right?
Yeah, it's insane.
Yeah, it is. Oh man, I had another follow-up question. Damn it. Oh, it'll come to me. Yeah, I was thinking about the whole deletion process. That's the thing I was going to say. So I know there've been times where folks have accidentally committed credentials or something into Git, right? And this is why it's important to really, just deleting the file doesn't mean too much, because someone could just roll back their history and oh, that's your AWS token. Great.
Yep.
Run into this, right? And this is, I think, one of those cases where you run git rm and there's some level of filter branch. Again, I don't understand how it works either. I just Google this every single time and then I just paste those commands. But this, right. Imagine what it's doing is it's basically changing the history, removing all references to any SHA that would hold that object, and then just nuking that thing altogether.
Right. That's right.
Okay, wow. That was super useful, and that was a whole bunch that I think it just...
Yeah. I'd be concerned that we overwhelm people with too much information, but
no, this is awesome. So it's just one of those things, and I would encourage folks after you listen to this, go fiddle around with your directory, maybe create a new Git repository, change a file, and there's another there's a video this is early from someone at GitHub. This is quite some time back. I'll remember to throw that in our show notes as well. But just after you've listened to what Gordon has said, just go meddle with your directory, see how things change. The thing that really had the aha moment was when I created a dummy repository. I added a text file, and then I started to see how it changed, right? Add, touch a file. So don't add anything, have empty content, and then see how that changes. Commit a file, see how that changes. Rename a file, and then see how some of these commits change, but some don't. Just looking at that you start to realize how elegant and beautiful a system Git is, despite how complicated it is. Because Git, like, famously it is purely meant for developers, right? Like, no normal sane human being would find this to be easy to work with or logical. Heck, even developers don't, right? So I think that really will help cement a lot of the stuff that Gordon talked about. This is awesome, G. Thanks a lot.
No, well, thanks for having me on. This is fun to talk about.
Yeah. If I'm sure folks are going to have follow-up questions and have more interesting things to ask, if they did want to do that, what's a good place they can hit you up?
Yeah, I'm on Twitter at G McCreight, GMCCREIGHT.
This is amazing. Thank you so much. This is always one of those things. I kind of understand how Git works, but I didn't have a better understanding of it. So I've always wanted to have this session with you. And I'm glad we could do this and share it with our listeners. And thank you again for spending the time. I know it's super busy at work for us, but you took the time and did this. I really appreciate it.
Well, sure thing, Kaushik.
All right. Thank you all so much for listening. And I will catch you in the next episode. I'd like to take this chance and thank the sponsor for this episode, educative.io. There are a lot of websites out there that offer programming courses, but educative.io has a really special text-based interface that helps folks learn faster and more efficiently. Check out the very new course they have for Android developers called Modern Android App Development. If you use the special link we have here, educative.io/fragmented, then you get an additional 10% off your purchase. So remember to use that special link. Once again, it's educative.io/fragmented. Thanks again for sponsoring the show. That's it for the show, folks. Fragmented is hosted by Don Felker and me, Kaushik Gopal. We edit and produce all the episodes here on Fragmented. Sarah the Amazing Jackson from the Spec Network helps with production assistance and wraps our final mix. Our theme and ad music is by the national recording artist Blueprint from Weightless Recordings. You can find more Fragmented episodes at fragmentedpodcast.com. Thanks for listening, and we will catch you in the next episode.